Welcome back to the classroom. My name is Mr. Wong. Today we'll be going through an exam question that goes through Module 2, Inquiry Question 1, and that's to solve for problems on inclined planes. Okay, it says the graph shows the motion of a 5 kg object on an inclined plane at angle theta. It says on the diagram, show all the forces acting on the box as labeled vectors. Okay. And just before we go through that, in the second question, it says the inclined plane is now slowly tilted more until the box just begins to slide. So at this point here, our block is stationary. Okay, so that's what we have. So what's actually happening here? We've got the gravitational force pulling it directly down, and we also have the normal force pulling it in this direction. That's 90 degrees to the surface. Now, because in this scenario we haven't mentioned that there is no friction, so that means this is a friction surface. So that means friction in this case here would be pulling our block in this direction like so to speak. Okay. Assuming that our block is to be sliding down in that direction there later on. But it's quite rare you'd come across questions where it exclusively is looking for friction. So if you were to just draw it as the gravitational force pointing it down, and then the normal force going perpendicular to the surface, that would be enough to get you the 2 marks here. All right, moving on to question B. It says the inclined plane is now slowly tilted more until the box just begins to slide. Explain why the box begins to accelerate down the plane. So this is what we have here. Now, part of the explanation, you can use the mathematical derivations to try and show for it. So obviously everything is in the component of the gravitational force. If we try and use a different color to just show for that, okay, so I'm just going to draw this side of the gravitational force again. We have this component, okay, we have this component coming down theta, the same angle that we have here, we're meeting it at a right angle triangle, similar because of our normal force component. So that's Fg. This sliding thing here, or this component of Fg, is going to be, let's say, the sliding force, so to speak. Okay? And this, if we were to try and derive it, that's sine theta, because this is the, let's see, so what we have here is we have the opposite side and we have the hypotenuse. So it'd be mg sine theta, mg being Fg, so mg sine theta. So how can I explain why the bigger theta, this box will begin to slide? Well, what we actually know is the sliding force that we have here, so to speak, should equal to the static friction force, right? So the bigger the angle, the greater the sliding force, and that can be matched by the static friction force until a certain point. Once the sliding force has become larger than the static friction force, then at that point on, the block can then slide down the inclined plane. So let's try and write something down for that. Okay, so what we can actually say is when the block is stationary, the component force of gravity, which in this case is mg sine theta, is smaller than the static friction force. Okay, so that's the scenario that we have here. However, once theta is increased, so however, when theta is increased, mg sine theta gets larger and becomes bigger than the static friction force. Hence, the block begins to slide down the slope. So that's what actually happens. You can think of it sort of in this direction here. If the block is not moving, then mg sine theta is a way of measuring the static friction force at that particular point in time. Once I begin to increase that angle of incline, then the sliding friction force, or this component here, will no longer equal this component here once the block starts moving. Okay, so you could say mg sine theta equals to static friction force in the scenario where the block is not moving, but if the block is moving, then that's no longer the case. Okay, I'll leave that there. If you found this video useful, hit that like and subscribe button, and I'll see you next time.